Hello guys, how are you today? So today I'll be explaining the physics, okay? And this is for term 2, week 3. Okay, and I'll start with the first question. A lightning what helps to protect tall buildings from being struck by lightning. It consists of a thick wet strip on the outside of the building connecting metal spikes at the top to a wet plate in the ground as shown in the diagram. So what you need to know is, like, in really tall buildings like in Burj Khalifa, whenever there's like lightning and whatever, the lightning is gonna strike always the tallest building first, and in Dubai the tallest building is Burj Khalifa. So what's gonna happen is the lightning is gonna strike Burj Khalifa first, so prevent the electricity or the electrons in the lightning to go and damage the building. They put something called a lightning conductor, okay, which helps to protect the building from being struck by the lightning. Now, what is it made of? It's made of a copper strip from the outside of the building, okay, and it's connected to metal spikes that leads it to a metal plate in the ground, so it's grounded so that the electrons they will come all the way down to the earth, because the spikes, okay, there is a positive stream of air. Okay, so what's gonna happen is that the electrons are gonna be attracted to the spikes and they're gonna continue their way down all the way until they are attracted to the ground. So this is how it works. So it is a copper strip on the outside of the building connecting metal spikes at the top to a metal plate. The metal plate is in the ground, so they will flow all the way down to the ground to the metal plate, and because the metal plate is a conductor, it will allow the electrons to spread further down the ground. Now, in question number 2, which of the following statements best describe an electric field? All you should know about an electric field is that it is a vector quantity, meaning it has a magnitude and a direction, okay, and that the magnitude of the electric field is denoted by E. It is equal to the force divided by the charge in Q. Okay, so this is then also correct. And I believe that the electric field is best described using lines. So magnitude and a direction, and this one. Now we move on to question number 3. Which statements are true about the role of charged particles in electric conduction? What we need to know is that in some semiconductors, after the electrons move, they leave gaps behind. These gaps can cause the conduction of electricity. Then, in an insulator, all electrons are fixed to specific locations, whereas in a conductor they can move. Especially in metals, the electrons can move. We call them free electrons. In conducting liquids, they have ions, that is cations and ions, positive ions, negative ions. And a conductor is usually a solid, okay, and it has electrons, not positive ions. Ions is only in conducting liquids like molten or aqueous. Question number 4. Which statements are true about the electrostatic paint spray gun? It's basically a paint spray gun that is charged negatively, so that it is repelled from the ground, but then attracted to the grounded surface. So let us say, for example, we have this wall over here. What they're gonna do is they're gonna ground this wall, so then the negative charges are gonna go, the electrons, let's say minus, they're gonna come from the wall, they're gonna go down to the earth, and it's left positively charged, okay? So what's gonna happen is that you're gonna have the paint spray gun over here, and these are the rays that are emitted from it. They are negatively charged, okay? Because they're negatively charged, they're going to be attracted to the positive particles and they are going to stick. And this is what, one advantage is that it leads to an even distribution of paint. It does not waste any paint. But we said the surface to be painted is grounded, whereas the charged particles are ionized. They are attached to the ionizing electrode. And then okay, and we said that these charged paint particles are attracted to a grounded surface, so because they are negatively charge, they're going to be attracted to the positively charged grounded surface because we removed the electrons from it by grounding it. So that's it. So question number 5, which of the following is referred to as an electric current? Electric current can mean the flow of electricity in a circuit. Now, or not even necessarily a circuit. It can be, for example, in an ionizing solution. In an electrolyte, you have here the negative, which is the cathode, and then here the positive, which is the anode, and then you have an aqueous solution. Okay, so then there is going to be an electric current in the water. It's going to create electricity. So because there is a movement of the positive charges, they will go to the negative side, and the negative charges will go to the positive side. So which of the following can be referred to as an electric current? It can be a flow of positive charges or a flow of negative charges. In general, a current is a flow of charges. Now we move on to question number 6. We should know that in a circuit made out of a battery, the electrons flow from the negative side to the positive side, and the current flows from the positive side to the negative side. So the electrons in the circuit move from minus, so we're going to start here, to plus. It goes in this direction, so from A to B. Now if we're talking about the conventional current, the current they are talking about, it's going to come from the positive to the negative in the opposite direction. So it's going to go from B to A. Okay? So electrons move from negative to positive, and the current moves from positive to negative, and electron and current flow in opposite directions of each other. Now this is an electric field. If you remember, we said the positive, the arrows are pointing away from it, whereas negative, the arrows are pointing towards it. Okay, so looking at S, you can see the arrows are pointing away from it, so that means particle S is positive, whereas T, the arrows are pointing towards it, so it is negative. U, the arrows are pointing away from it, so it is also positive. V, the arrows are pointing away from it, so it is as well positive. So the answer is positive, negative, positive, positive. Question number 8. The electroscope shown below is positively charged by a glass rod. The gold leaves of the electroscope spread out of the way from each other. So what happens is that they bring a glass rod, and we know that the glass rod is positively charged. Okay, what's gonna happen is that initially these gold leaves, they were laying down. Okay, they had the same number of charges, so let's say 3 positive, 3 negative, 3 positive, 3 negative. So they are neutral and there is no force between them. Now when you bring this positively charged rod, of course it has a stronger positive charge than these ones at the bottom. So then the electrons are going to move to the top, and they're going to accumulate from the top, or they're going to accumulate at the top. And we are going to be left with the electrons at the top and 2 positively charged leaves. So if positive and positive, same sign, they are going to repel and they are going to diverge away from each other. Then they told us when they brought another charged rod W, okay, close to the metal knob, the gold leaves come close together. So what could we potentially bring that will bring these leaves close together? So what happens if we bring a negative charge? We already have an accumulation of negative charges on the top. So the negative charges are going to repel these, so they will come down and they will balance these out. So then you are left with 2 neutral leaves, which then they will not attract each other, but they will fall because there is no force of attraction. So we will say negative because the charge on W was negative, it repelled the negative charges. So now we move on to question number 9. In a circuit, 3 coulombs of charge, 3 coulombs of charge flow each 0.6 seconds. So they need the current. What we need to know in this equation, that the current, denoted by I, is equal to the charge Q divided by the time T. So we have 3 coulombs, which is the Q, 3, divided by the time, which is 0.6 seconds. And if you do it on your calculator, you are gonna get 5. So the current in the circuit is 5 amperes. If we move on to question number 10. Okay, now in question number 10, what they are saying is really important. Although charge cannot move through the body of the insulator, I'll just write the answers for now. Charge can be slightly displaced within each atom, resulting in a net induced opposite charge slightly nearer to the inducing charge. So here they are introducing to us charging by induction. So let's say you have a neutral plastic ball, and we all know that plastic is a good insulator. So even though it is an insulator, so the charge cannot move through the body of this object, it can be slightly charged, or the charge can be slightly displaced within each atom of this object, because this is an atom in one big object. So like the atoms are way smaller. So let me draw maybe an accurate representation of how an atom is. All of this, let's say, is a cell, and this is an atom compared to the cell. So they're really, really small, but inside of the atom we have positive and negative if it is neutral. Now in the insulator, they told us it does not allow the charge to flow through it, but you can charge the atoms by inducing the charge. So you slightly bring near to it, for example, a negatively charged rod. So what's gonna happen is that the positive will become polarized, so then it will switch to the positive side, okay, and then it is technically positively charged. So at this case, it becomes a positively charged plastic ball. That doesn't make sense though, because plastic is negative. But in some cases, let's say you brought next to it a negative charge, and by induction, it can become positively charged. So you're not touching it or anything, you are introducing the charge to it. And so then polarization will happen, it will flip, okay, the faces will flip, and then it is technically positively charged. Now label the charges in the sketch of an atom below. Remember, you have to use it in singular form. So this is a neutron, this is an electron, and this is a proton. I think this is one of the easiest questions. Inside of the nucleus is proton, outside of the nucleus is electron. Question number 12. A what charged particle is a particle that gained electrons? Gained electrons means it becomes negatively charged, because electrons have a negative charge. Now, a what charged particle is a particle that lost electrons. Positively charged particle is one that lost electrons, because losing negative charge means you become positive. Alright, so now we move on to question number 13. Which of the following is true about the Van de Graaff generator? So let's read them option by option. The Van de Graaff measures the electric forces acting on a material. Definitely not. However, it does produce enormously large static electric potential. So what happens is that the rubber at the bottom of the Van de Graaff becomes negatively charged, which leaves the positive charge accumulated on the top of the sphere, and then we do grounding or earthing, and then the negative charges are gonna go to the earth, okay, or to the bigger conductor, and then we are gonna be left with a positively charged Van de Graaff. So this positive charge is accumulated on the dome of the Van de Graaff. The dome of the Van de Graaff is like the sphere of the Van de Graaff, and then we call this static electric potential. Now, it generates intense magnetic fields. No, it's not magnetic. It creates electric fields. It charges neutral materials by electrostatic induction. No, it is not electrostatic induction. You touch it and then your hair will stand up. So it charges neutral materials by conduction, not electrostatic induction. It is made up of a lower roller, which is the negative, or the rubber that creates the negative, and then a dome that acts as a collector. Now, we move on to question number 14. Write the equation of the electric field at a point in terms of charge Q at that point and force F it experiences. Okay, very simply, what you need to know is that the electric field E is equal to the force F divided by the charge Q. Okay, so now we move on to question number 15. This is easy. If the arrow is pointing away from it, it is positive, and if it's pointing towards it, then it is negative. So then, number 16, scientists have agreed to adopt the convention that the current, okay, remember the current always flows from the positive side to the negative side of a generator or a battery, and the electrons flow from the negative side to the positive side. Now, objects become charged when they gain or lose electrons. Electrons have a negative charge, protons have a positive charge, and an object that gains electrons acquires a negative charge. We move on to question number 18. Remember, any neutral object is attracted by a positive or negative charge. So, as long as it's neutral, okay, and you introduce it first to a charge, it will be attracted to that charge. So, the sphere will be attracted to the rod. Now we move on to question number 19. Now I got some comments that I didn't explain this in a way last time. I explained it in a different way, and that way was just like easier for me, but then I forgot to explain how I got that way. So let me explain to you how I get that way. We have the equation F is equal to the constant K multiplied by the charge Q1 multiplied by the charge Q2 divided by the distance squared. Okay? Now, what I did as a rule, or what I remember reading somewhere, is that the force is inversely proportional to the distance squared. So, if I multiply the distance by 2, I'm gonna have to square it, so it becomes 4 distance squared. Okay, so now since I multiplied the distance by 4, that means I'm gonna have to divide the force F by 4. Okay, however, with the quantity Q, the F is directly proportional to the quantity Q1 multiplied by Q2. So if I multiply this by 2, it's gonna be multiplied by 2. If I multiply this by 5, it's gonna be multiplied by 5. However, if I multiply both of them by 4, it's gonna be multiplied by 4 2 times, so it's gonna be multiplied by 16. Okay, and because of that, I made a relation that the force between two equal charges is distance. This is the distance 1, the initial distance. And this is the initial force, force 1, which is 1.2 millinewtons. Then they told us if the distance between the charges is decreased to 0.5 centimeters, so this is now distance 2, how much will force 2 become? So making it as a relation, what I did was I took distance 1, and we know that the distance is always squared, so I squared distance 1, then I divided it by distance 2. So divided by 0.5 squared. Again, distance 1 squared divided by distance 2 squared. Now, as an answer on your calculator, you are gonna get 16. Now, what do I do with this 16? This 16 means that I divided 2 squared by 16. So I divided the distance by 16. Now, what does that mean? We said that the force is inversely proportional to the distance. So if I divided the distance by 16, that means I'm going to multiply the force by 16. So it becomes 1.2 multiplied by 16, and that gives us a value of 19.2. So F2 is 19.2. So the answer is 19.2. Now we move on to question number 20. Okay, this is a Van de Graaff generator. What happens that in the bottom, it acquires a negative charge that will build a positive charge in the dome. And then you earth the charge so that the negative charge is gone. And you accumulate a positive charge on the dome, which is the static electricity accumulated by the Van de Graaff generator. Now, this is direct application. We have electric field E, we have the quantity Q, and we have the force F. Okay, E is equal to the force divided by the quantity. We need to find E. It's equal to the force 2.4. This is micronewton, so that is 10 to the power of negative 6 divided by 30, and this is nanocoulomb times 10 to the power of minus 9. So doing it on our calculator, 2.4 times 10 to the negative 6 divided by 30 times 10 to the power of negative 9, we are gonna get 80 newtons per coulomb. If we move on to 22, this is also a direct application, but we know that the current flows from a positive to negative, or the opposite direction of the electrons. If we read, it says, electrons of 20 microcoulomb charge are transferred from metal plate A to B. So the electrons move from A to B. That means the current will flow in the opposite direction, so from B to A. So from plate B to plate A. Now, to find the current, we know that the current is I, and we also know that the current is equal to the Q, the quantity of charge of electrons, divided by the time. Okay? Now, of course, we have to change it into its proper values. So we are starting off with 20 times 10 to the power of minus 6 coulombs divided by 5 times 10 to the power of minus 3 coulombs, and minus 3 seconds. So we are gonna get 4 times 10 to the negative 3, and this is in amperes, but if you notice, they need it in milliamperes. So to change it from amperes to milliamperes, we need to multiply by 10 to the power of 3. So these two will cancel each other, and we are left with 4 milliamperes. So let's submit, and hopefully there are no mistakes. And thank God there are no mistakes. Thank you guys for watching, and I hope you had a wonderful day. I hope you enjoyed, and have a wonderful vacation.